What do I mean by assurance? What I mean is that contracts do what they should do and don't do what they shouldn't. So, and we do this in a number of ways. We make the language as simple as it can be, so it's not difficult to use, it doesn't have odd nooks and crannies like some languages I could mention. Contracts are readable, and we can simulate the contracts easily. So you can try out a contract before you work with it. In fact, we can do more than that. We can explore not just one route through a contract, through the different options there might be. We can explore every route, and I'm going to explain a bit more about that in this towards the end of the seminar. And then finally, there are things we can actually mathematically prove certain sorts of safety properties for the Marlowe system. And again, I'll talk about that at the end of the presentation. But let's get started. And I think the best place to start is to think, what does a financial contract do? And if we look at what financial contracts do, they'll have a number of participants, and they'll pay money into the contract. The contract, at certain points in the evolution of the contract, decisions might be taken. Should the contract be sold, or should I stick with it? Also, external information from oracles, from stock exchanges, from currency exchanges can be fed in, and that determines what the contract does next. And also, contracts can pay out to participants. So payments in and out, decisions, external information feeding in. So there are actions like paying in and decisions, and there are other processes the contract goes through that can happen automatically. And the final thing that we have with Marlowe is that we can represent ownership of a particular role by a token on the Cardano blockchain. So we use tokens to represent ownership. So transferring a token means transferring ownership of the contract. I'm not going to say much more about that today, but this is something that makes the language really quite powerful. The contract, a running contract, is a financial instrument that can be traded. Okay, what about designing Marlowe? What have we done in doing that? Well, we call a smart contract, but in fact it's a program running on a blockchain. And programs could do all sorts of terrible things. They could run forever. They could wait for an input forever. They could terminate holding some of your crypto assets, or they could in principle double spend your assets. So what we wanted to do was design the language so those things can't happen. We built the language so contracts are finite, there's no recursion or looping in Marlowe itself, so contracts are guaranteed to terminate. Any sort of action, a choice, making a deposit in the contract, has a timeout, has a deadline on it. And we can predict how long the contract is going to last by reading off the timeouts, reading off the deadlines. And we've designed the language so when the contract closes, any money left in the contract is refunded to whoever it belongs to, and that's modeled by accounts inside the contract. And finally, value is conserved, and that's guaranteed by the underlying blockchain. So we get some things from the blockchain, but most of the properties I'm describing here are properties of Marlowe as the language and system. So these, when I flash up a blue background, these are assurances. Contracts are finite, contracts will terminate in a defined time, no assets retained. So what does the language look like? It's really very simple. Here I'm saying there are 6 different things we can do in the contract. And let's run through some of those. The contract can make a payment. A party can pay a payee a certain amount of money, asset, and then carries on as another contract. Making an observation, something in the outside world, or a choice, can lead us to choose one of 2 contracts, a then contract and an else contract. If the observation is true, we do one thing. If the observation isn't true, we do the other. The most complicated construct is the when, and a when waits for a number of actions. That can be depositing money, receiving an input from an oracle, making a choice. So things that when the outside world impinges on the contract, we have a number of possible actions. When an action takes place, we execute the corresponding contract. So we have these action, if this action happens, do this contract. And one of a number of actions could take place, but, and this is the bit of the design, there's a timeout, there's a deadline. At that deadline, we execute this contract, so we don't wait forever for inputs. And finally, we have the close construct. And what happens on close is we refund any money that the contract is holding on to. So there's that guarantee built in to how we implement the language. Now, what does Marlowe look like? What's the engineering? What's the environment it sits in? Marlowe is this special purpose language that sits on top of Plutus, the general purpose language for programming contracts on Cardano. And both of them are built using Haskell. Plutus is a version of Haskell adapted for the blockchain. Marlowe is described in Haskell. And they interact with the real world through oracles, but also, and I'll talk about this in a second, they interact with the user through a end user code, which we call Marlowe Run. And you may have seen our demo of Marlowe Run on a Cardano 360 last week. So what does running a contract look like? There are two parts to it. The contract puts transactions onto the blockchain, and we have a thing called the Marlowe interpreter that runs as code on the blockchain that checks that these transactions are valid for that Marlowe contract. So we verify that we're adhering to the contract on the blockchain itself. But where do those transactions come from? They come from off-chain code. They come from Marlowe Run, the end user client, interacting with a wallet. So there are transactions generated off-chain, they get put onto chain, they get validated on the chain, and also Marlowe Run, so there's information flowing from off-chain to on-chain. There's also information flowing the other direction because other participants in the contract may have made a deposit, made a choice. We need to inform all users in that contract, all participants, that choice has happened. So we have this two-way flow of information, off-chain, on-chain, and off-chain again. So that's a very high-level picture of how Marlowe works. Let's now talk about some of its nice properties. I've talked about usability. One of the ways that we've tried to make Marlowe as usable as possible is by offering authors various different ways of writing contracts. So we'll look at that in a moment. But we also allow people to explore how contracts work before they're run, and that's in a simulation. So so we've got authoring, different methods of authoring, some involving code, some not, and simulation, allowing you to understand a contract before you commit to it. So how do we author Marlowe contracts? One way of doing it is visually. We have a version of Marlowe in a language called Blockly, a language of blocks, and you can edit Marlowe contracts visually using that. If you do code, you can build Marlowe programs using facilities of Haskell or using the facilities of JavaScript. What we've done is we've so-called embedded Marlowe in those languages, so you can use those language features when you're writing your Marlowe. And finally, we've got ways of generating Marlowe contracts from the Actors Financial Standard. I'm not going to say anything more about that. But what can we do when we've written a contract? In the Marlowe playground, you can simulate the action of the contract, step by step, the action of the contract. You see here on the right, you're being offered a particular action that a participant is paying for an item that's being sold in this escrow contract. You can, by clicking the plus button, you can choose to do that. If you click undo, which you see there, you can revert the last step that you took. So you can take a step, take another step, but step back. So you can explore different paths through the contract. and reset takes you right back to the beginning. Now we're in the process of redesigning this, and so that the simulations inside the playground, Marlowe Play, will look much more like the simulation, the view of a contract that you see in Marlowe Run, which you might have seen on the C360 last week, and which we're going to be releasing in prototype in a few weeks' time. Now, we talked about usability, but we've morphed a little into assurance that simulation gives you a way of understanding what contracts do. How else do we provide people with assurance for Marlowe? Well, we use the power of logic. We can do what's called static analysis. So we can automatically, just at the push of a button, verify that a particular contract has properties that we want. And also, we can do heavier weight work, what's called machine-supported proof, machine-checked proof of properties of the system itself, not just an individual contract, but the whole system. Now, let me talk about static analysis first. What static analysis allows us to do, because Marlowe programs are simple, it means that we can check every execution path through a Marlowe contract. Not just one, not just two, not just testing, but every path, every choice of timing for submitting a transaction. We can explore all of those. For example, we can ask the question, is it possible there may not be enough money to pay for a pay construct in the contract? So could the contract fail to deliver a payment? When we can ask that question, the system will answer, and what's more, it's what we might call constructive. If there is a way it could go wrong, the system shows us how that could happen. It gives us what's called a counterexample. So we're able to pinpoint how the contract can go wrong, and so then we can fix it, make sure it is fixed in a way that we avoid that. Or, we live with it, we know that situation is there, but we can make choices in order to avoid it, for example. So that's what static analysis gives us. Checking all execution paths, all choices, so we're getting a complete guarantee, not just a few tests, but a complete guarantee. And you can find this in the Marlowe playground. You can see an example here. There's a contract running where one of the initial steps is for Alice to make a deposit of 450 Lovelace. And if she does that, the contract will run. There won't be any way the contract can go wrong. And you see that in this snapshot here. Now, if we change that 450 to 40, you will see, on the other hand, that this can go wrong. We get a transaction partial payment, and it tells us that the problem is that payment initially was not enough to make a corresponding payment later on. Now, finally, not just individual contracts, we can claim that certain aspects of the system are safe. We can, for example, take the code that we have that describes how Marlowe works, and we can say an account in a local account in a contract will never be negative. You can never overdraw, if you like. And we can also establish that money is preserved. So the money that is fed into a contract is the same at any time in contract execution. Some money will be held inside the contract in the accounts, and some money will have been paid out. And the money that's been paid in is equal to the sum of those two. So all the money paid in is either still in the contract or has been paid out. On the right-hand side of the slide, that's a bit more technical. We can prove things that underpin the static analysis I talked about earlier. So we can show formally, mathematically, that the static analysis we do is bound to find any error that exists, and it won't report any, there are no false positives, there are no false negatives. So we're getting the ability to establish properties of the whole system once and for all. And we've not started this yet, but this is work in progress. We can do the same for individual contracts and templates too. We get some guarantees from the static analysis, but we can prove more properties using this kind of mathematical machine-checked proof approach. So let me summarize. I've said Marlowe, it's a special purpose language for financial contracts, designed for users. So we present, as you've seen, ways that users can interact with existing contracts, explore those contracts, ways that users can develop contracts visually without writing any code, or using a language like JavaScript if they wish to. And we provide levels of assurance. Contracts are readable, they're simulatable, as I mentioned. We can explore all the behavior of a contract without running it, and we can prove the system to be safe in various ways. And if you want to try out Marlowe in the playground, here's the URL to go to, play.marlowe-finance.io. And as I said, in a few weeks' time, we'll be releasing a prototype of Marlowe Run, so you'll also be able to try that system out. And we're working hard on updating the Marlowe Playground, adding more features to Marlowe Run, so that when we release Marlowe running on Cardano later in 2021, we'll have a full suite of tools for you to use to build and run financial contracts on the Cardano blockchain.